Hi, everybody. Okay. Everybody, anybody have any questions at the moment before we get started? Okay. One comment is that I have to cancel office hours today. I sent out an email earlier about it. Okay, so let's pick up where we left off last time. Share my screen. Okay. So last time we defined the exterior measure. So let's put this definition back up. Exterior measure on RD, or outer measure, so we'll call this the outer measure. If E is a subset of RD, any subset, the exterior measure of E is given by the following expression. So mu star of E is defined to be the inf over all countable, at most countable coverings of E by closed cubes. Is over all countable coverings so E is inside the union from j equals 1 to infinity of the QJs. So you take your set, you cover it any way you like with a bunch of closed cubes of different sizes. You can use infinitely many of these as long as you're using countably infinitely many cubes. And then you sum up all of the volumes of the cubes, which is something we know how to compute, right? We know how to just, a cube, we know how to compute its volume. And then we just take the inf over all of such coverings. So this should remind you of things you do in calculus, right? Okay, so it's not a mysterious definition in any sense of the word. Okay, but now we have this definition, and we're going to try and build up like some working understanding of it. And we started last time. And let me just continue with a couple of examples. So some more examples. Many covered last time. In lecture 11. So I can't remember which number example this is. But one is if that the exterior measure of RD is infinite. And this is clear, kind of, because you could just, it's bigger than any the exterior measure of any cube. I mean, you can just take larger and larger cubes. Another example of a set that we understood, so was the Cantor set. So Cantor middle third set We kind of did this last time, but we can see that so this is called C, mu star of C is equal to 0. So the Cantor set has, middle third set has measure 0. And the proof of this last example is just that C is inside of each of the finite collection of intervals CK, which is a disjoint union of 2 to the k cubes. In this case, these are just intervals of length each of length 3 to the minus k, which means that the exterior measure of C is less than or equal to such coverings. In particular, one such covering is just each. This is kind of built as an intersection of these sets CK, or it is an intersection of these sets CK. So each one of these is a covering by finally many closed cubes. So the exterior measure, which is the inf over all such coverings, is less than or equal to the volume of this covering, which is just 2/3 to the minus k, which goes to 0. Sorry, to the k. 2/3 to the k, as k goes to infinity. So this is true for every k. Okay, so the Cantor middle thirds set has exterior measure 0. All right, let's stop with some examples now, and rather now start deducing some general properties. We're just going to keep building on these examples, but what we want to start getting towards is understanding how this behaves under properties like additive. In what sense is this exterior measure additive? So additivity properties, etc. So we're gonna try and get there. So properties. So these are more abstract properties of the exterior measure mu star. Property 0 is that. So this is maybe just a technical property, but it'll come in handy just from the definition. For every epsilon bigger than 0, there exists a covering by closed cubes, possibly finite, such that the sum over j equals 1 to infinity of the exterior measures of the closed cubes, which are just these volumes, I guess. Maybe I should put it like this. Is less than or equal to the exterior measure of E plus epsilon. Right, and this is just from the definition because this object is the inf over all such objects. So in particular, if this is the inf, you can find a particular covering so that you have this is of course true, but you get in between the exterior measure of E and an exterior measure of E plus epsilon. Right, you can get arbitrarily close to it. You can find a covering that nearly realizes this inf for any epsilon bigger than 0. So this is just from the definition. Okay. Property 1 is monotonicity. Namely, if I have two subsets, E1 and E2, and E1 sits inside of E2, the subset, then mu star of E1 is less than or equal to mu star of E2. right? This is also immediate from the definition, right? Because any covering um, of E2 is also a covering of E1. So whatever the inf is for overall such coverings that gives us mu star of E2, the collection, we can just take a strictly larger collection of coverings of E1, and so this inf is necessarily smaller or equal to. Property 2 is countable subadditivity. What does this mean? That if E is the union over a possibly infinite collection of sets EJ, so if E is a union of sets where the EJ might be overlapping, then the exterior measure of E is less than or equal to the sums of the exterior measures of the EJs measure. Okay, so this requires some proof, but the main ingredient is going to be this property 0, namely that we can almost realize the inf in the definition. So it's the proof. Let me sync my Dropbox folder. Okay, well, just one comment. Without loss of generality, we can assume that mu star, that each of these is finite for every j. Since if one of them is infinite, then the inequality obviously holds, right? So we can reduce the case when each of these is finite, and the exterior measure of each of the EJs is finite. Then for every covering of, or so let me phrase this differently. Then for every epsilon bigger than 0, find a covering QJK, where this is a collection of closed cubes with a new index k that cover each of the EJs, covering EJ, and such that the sum from k equals 1 to infinity of the volumes of the QJKs is less than or equal to the exterior measure of EJ plus epsilon, and then I'm later gonna have to sum over all j. So I'm going to make this smaller than an epsilon I start off with. I'm gonna in fact make it much smaller. I'm gonna weight this by 1 over 2 to the j. As you can see later, I'm gonna want to get something summable. I'm gonna have to sum up everything here. So I can do this, right? I just pick I fix a j, pick my epsilon to be epsilon over 2 to the j, my small number to that, and then I try to, and then I pick a covering that gets me just below mu star of EJ plus epsilon over 2 to the j. Then E sits inside of this double sum from j equals 1, k equals 1 to infinity of the q jk's. Right now, if I take this whole sum, E sits inside of them, since each of these collections of QJs cover each EJ, and the collection of EJs cover E, this whole thing covers E. So this is a covering of E by closed cubes, and which means that mu star of E, the exterior measure of E, is less than or equal to the sum over all j and k of the volumes of the QJKs, which is equal to, this is just equal to a double sum, right? This is equal to the sum from and I've built these so that this inner sum satisfies this inequality, right? So this is less than or equal to the sum from j equals 1 to infinity of mu star of ej plus epsilon over 2 to the j. And this in turn is less than or equal to the sum from j equals 1 to infinity of mu star ej plus what I obtained by summing up epsilon divided by 2 to the j. And if I just sum up from j equals 1 to infinity to 2 to j's, I guess get 1 plus epsilon. And now I'm done, since this inequality now holds for every epsilon bigger than 0. It's arbitrary. Okay. So that now, so we just proved again that we just proved this property of countable subadditivity. The exterior measure of a set is smaller than or equal to the sum of the measures of the sets in any covering. Okay, property 3. Is that if is an alternative characterization of the exterior measure. So for any subset of RD, the exterior measure of E is equal to the inf over all mu star O's, where inf is taken over all open sets O such that E is inside of O. So rather than coverings by closed cubes, you can instead take define the exterior measure as being just an inf over the exterior measures of open sets containing a set E. Okay, what's the proof of this? By monodicity, by property 1, this inequality is clear. Right, because this is true for every open set. This inequality is true for mu star of E is less than or equal to the mu star of every open set that contains E. So then it's less than or equal to the inf. So of all those numbers. But now choose, we want to obtain the opposite inequality. So choose epsilon bigger than 0. Or not choose epsilon bigger than 0. Never do that. So let epsilon bigger than 0 and choose Qj such that E is inside union of Qj's. So now we're going to choose one of these almost realizers of the inf. So cubes Qj's such that sum from j equals 1 to infinity of the volumes of the Qj's is less than or equal to mu star of E plus epsilon over 2. Now let Qjo be equal to an open cube for each j containing Qj. So I'm going to turn this almost inferializing cover into an open cover by just taking slightly enlarged open cubes containing each of the QJs. Open cube containing QJ such that the volume of QJO is less than or equal to the volume of QJ plus epsilon over 2 to the j plus 1. I'm going to trust my notes that this normalization is the right one. Then the point is that if I take a countable union of open sets, I still get an open set, right? Then O equal to the union of the QJOs is open. And because openness is preserved under countable union, and use for O is less than or equal to, this is by the previous property, countable subadditivity. The sums of from j equals 1 to infinity of the QJOs, which in turn are less than or equal to the sum by construction measure of the QJs plus epsilon over 2 to the j plus 1, which is less than or equal to the sum from j equals 1 to infinity QJs plus epsilon over 2, which is less than or equal to, by construction, remember I chose these QJs in the outset to satisfy this property, so I had another epsilon over 2 there, which is less than or equal to mu star, remember these almost gave me mu star E, plus epsilon over 2 plus this other epsilon over 2. Again, this holding for every epsilon bigger than 0. So what we proved again now is that an alternative way of finding the exterior measure of the set is just taking an inf over all open sets, the exterior measures of all open sets containing it. Any questions so far? Okay, property 4. Now here we're getting into some real meat. If you have a set E, which is the union of two sets, E is union E, union E1, union E2, and the distance between E1 and E2 is bigger than 0, yeah. If these two sets just have positive distance between them, then the exterior measure of E is equal to the exterior measure of E1 plus the exterior measure of E2. All right, so this is additivity, but when we have a fixed distance between the sets, if the distance between the sets is positive, so then we have this additivity of the measure. Proof. So we already know right. We already know countable subadditivity, so particularly we know the subadditivity property. And now let's try to prove the opposite inequality. So, well, these sets are a fixed distance apart, so I'm going to quantify this. I'm just going to say find a delta bigger than 0 such that the distance between E1 and E2 is bigger than or equal to delta, which is a positive number. I know this is a positive number. I'm going to tell you how big of a positive number is. They're delta apart at least. And now choose a covering. E inside of a covering of E by rectangles, or by closed cubes, rather, by closed cubes, such that this is almost realized. So we have a collection of closed cubes that almost realizes the exterior measure of E. But now, okay, now let's just take this collection of cubes and chop them up. So now subdivide each qj. We can assume, and by subdividing can assume that each, so after subdividing and then relabeling, that each qj has a diameter less than delta. So what does this look like? We have E1, E2. These are at least delta apart. And then we just make sure that our cubes have diameters less than delta by possibly chopping them up again, like this. Okay, but now each cube in this collection of these QJs only intersects, can only intersect either E1 or E2, but can't intersect them both, right? Because if a cube intersects E1 and its diameter is less than delta, then it can't reach E2, and vice versa. So each cube QJ can only intersect E1 or E2, not both. And now just divide up my indices. J into groups, J1, J2, where E1 is inside the union J1 of the QJs, and E2 is inside the union of those QJs from the index set J2. And I want these index sets to be non-overlapping. So the intersection is empty set of the index sets. Then mu star E1 plus mu star E2 is less than or equal to the sum over all J1 QJ plus the sum for all J and J2 of QJ, because each one, this one covers E1, this collection covers E2. So this inf is bounded above by this object, and this inf is bounded above by this object. But now these are disjoint index collections, so it's just the full sum, which is equal to QJ, which by construction was less than or equal to mu star v plus epsilon. So now we have, this holds for every epsilon bigger than 0, so it holds without epsilon there as well. Any questions about this?
Sorry.
Yeah, one at a time.
Go for it, Samuel.
Just want to ask, can we weaken the statement to just having E1 and E2 disjoint?
No, and that's going to be the crucial. That's going to be the key thing. So I put this either on your homework or this week. I think it's for your homework due next week. So this is going to be the thing that trips us up. We'd like it to have our measure to have this property, right? If we have two disjoint sets, then this additivity holds. But it doesn't work for exterior measure, and you can build a counterexample from the example of non-measurable sets that I gave in the first class of measure theory. So this is going to be the distinguishing issue with trying to, because now you might start saying, well, the exterior measure sounds like a good candidate for the measure, right? We're getting close to proving all the properties we'd like to have for a measure, except we'd like what you just said. We'd like this to hold without this hypothesis that their distance is positive. We'd like it to hold just if they're disjoint, and we're not going to be able to quite prove that. In fact, it's false. So we're going to have to do something to go. This is why we're calling this an exterior measure, because we're going to have to take one more steps to go from exterior measure to a measure, and to get the property that you'd like to prove, like that you mentioned. So disjoint sets have then additivity holds for the measure.
Yep, thanks for that.
I also had a question about the step where we subdivided the closed cubes.
Yeah.
So does that require that we restrict again to the case where the measure is finite? Because otherwise we might not be able to subdivide into countably many smaller cubes?
Hold on 1 second. I'm thinking. So even if it's infinite, right, we could still do countably many smaller cubes, right? Or you just take a grid. You could just take a grid of RD. I'm trying to remember what we proved about, but I'd like for those measures just to be equal to each other, right? That what I want for the subdivided property, subdividing, that I still maintain this property of the collection, and yeah, and last class we proved what did we prove? We proved this for finitely many rectangles. Yeah, so I guess maybe so I'm kind of using this property, right? That I can just the sum of the measures of the subdivision of the thing is equal to the measure of the thing of the cube that I started with. So here, this is for finitely many rectangles, and let's see what else if we proved anything.
Well, I guess each cube you subdivide, you're subdividing it into finitely many because the size is limited, so it should still work out, I guess.
Yeah. Oh, thank you. Yeah. Yeah.
Okay, thank you.
Yeah. Yeah. Thanks for your help at the tail end of that. Yeah. Yeah. So I guess we don't like so to finish. I get just to clarify. I guess we don't need to assume that here that the measures are finite. Okay. So um, so we're almost there. So property 5 is that if my set is equal to QJ, a union of cubes that are countably disjoint. So countable, so rather almost disjoint. Countable union of almost disjoint. Almost disjoint, remember, means that their interiors are disjoint. Almost disjoint cubes. Then mu star of E is equal to the sum. Now we have true additivity here of the measures of the QJ, of the volumes of the QJs. So if my set is just happens to be given by is equal to such a countable union, then the exterior measure is like this. Proof. And let me just maybe before I prove this, let me highlight. Remember, one of the first things we proved was this characterization of open sets in RD. That every open set in RD was expressible as such a union, a countable union of almost disjoint closed cubes. So in particular, remember we said, okay, well, a good candidate for the measure of such of an open set then would be just to sum up all the volumes of this collection of disjoint closed cubes. And in this proposition, but we were worried, okay, if we did that, then it was unclear if the size of the measure of the open set was dependent on which countable union of closed cubes we chose. This is now proving that this is independent. The exterior measure is independent of which countable disjoint union of closed cubes we chose to cover our set, or to be equal to our set, or open set. I'll say that again at the end. So let's prove this property. So at QJ, we have these QJs, which are closed almost disjoint cubes. Let QJ twiddle be cubes strictly inside QJ. So, i.e. the QJ twiddles inside QJ for every J, and such that the volume of QJ is less than or equal to the volume of QJ twiddle plus epsilon over 2 to the J. We're going to do this trick again. Okay. Then now we'll apply previous property for repeatedly for each of these over and over again. So let's apply property 4 repeatedly. And note that, so noting each of these QJ twiddles is at fixed distance from another. And we're okay, we'll have a fixed distance between all of them, a uniform distance between all of them, as long as we just only work with a finite collection of them. So, which means, for every n bigger than 0 but finite, it's important that we do this when we finite numbers of these guys, mu star of the union from J equals 1 to n of the QJ twiddles is equal to the sum from j equals 1 to n of the qj twiddles. Right, we just, this is by a previous property we proved. For each fixed n, we can find the delta such that all of these sets are bounded, have bounded distance, have a uniform bound away from each other. Which is bigger than or equal to the sum from j equals 1 to n of qj minus epsilon over 2 to j. Right, where, because the qj twiddles are picked like this. So now I just subtract epsilon from both sides. Okay, but since the sum from j equals 1 to n of the qj twiddles is inside of E, right? Remember, E was equal to the union of the qj's. The qj twiddles are smaller, so we no longer equal E, where we have their union is inside of E for every n. For every n, we have that mu star E is bigger than or equal to the sum from j equals 1 to n qj. We can sum here, right? Since I picked 2 to the j, this is epsilon over 2 to the j, so after summing, we pick up an epsilon minus epsilon. This holds for every n. Now we'll just let n go to infinity and obtain qj. So this is the hard direction, and this is already proved. Okay, so there we go, and let me just emphasize this conclusion conclusion is that if set is almost disjoint union of closed cubes, then the exterior measure is just equal to the sum of the qj's. This implies that every open set has exterior measure given by such a formula, right? Because we proved already that every open set is expressible as a countable union of almost disjoint cubes, which then implies that the sum is independent of the decomposition. So this exterior measure, so that work we did of characterizing open sets as sums of as unions of almost disjoint cubes, closed cubes, was worthwhile because we can compute this exterior measure that way. And a corollary of this is that simple sets with volume calculated by integration. So remember, in calculus class, you used to in your vector calculus class at some point, you probably started computing the areas of sets by integrating the function 1 over that set. that volume that you used in calculus, that you defined in calculus, is exactly given by the exterior measure of such a set. So, and remember in calculus, so if you remember, the set had to be bounded by a nice, had to be relatively nice set to do this integration, right? Like the boundary of the set was some nice, and R2 was some nice closed curve or something like that. Simple sets with volume calculated by integration. Is equal to the exterior measure of those sets. So not only is exterior measure not a crazy concept for measuring things like cubes or open sets, but from this formula we see that that all the sets that you talked about volume for in your calculus class, the volume that you were talking about then is exactly the same as exterior measure. So this is the type of like sanity check you want to make when you're thinking about generalizing the notion of volume. You want to make sure that it kind of agrees with your intuition about what volume is. So remember, in calculus, you can compute the volume of sets like this by integrating the function 1 over this domain like this. It's A, so volume of A. Dx. Okay. Okay. However, getting back to Samuel's question from the beginning, we have not proved that the exterior measure of E1 union E2 is equal to exterior measure of E1 plus the exterior measure of E2 for E1 union E2, a disjoint union. Right, we needed to assume that the sets had positive distance from each other to prove the statement. This is not true for some pathological sets. So, and you're gonna work on this next week for your homework to build such a union, a disjoint union of two sets for which this property fails. And the candidates are the set N we made that was sort of nonsensical during the first discussion on measure theory. Okay, so exterior measure is very nice. It agrees with our the notion of volume from calculus. It has this nice property that we were just careful with the definition, and we can then show that once we express an open set as a disjoint union, almost disjoint union of closed cubes, then the measure of the open set, exterior measure of the open set, is just given by summing up the volumes of each of those closed cubes, making up the open set. But we don't quite have this property here, which we want. So we're going to make one next definition to clear us the way there. So we're going to define what's called the Lebesgue measure. On RD. So definition is we're not going to define something new. We're just going to declare which sets are measurable, and we're going to make this declaration in a way that's going to allow us to recover this property. Okay, the definition is that a subset E in RD is Lebesgue measurable if, or just measurable, or we just say measurable. If for every epsilon bigger than 0, there exists an open set O such that two properties hold. One, O contains E, and two, the exterior measure, the concept we just defined, of O take away E is less than or equal to epsilon. So for every epsilon, you need to find an open set that contains your set, and such that the exterior measure of that open set minus your set is less than or equal to epsilon. So it's kind of like thinking that this open set really captures everything in the set. So, and I just want to note that this is pretty subtle. Right, 1 second, let me just sync this. This is pretty subtle, and I want to compare it with a property that that we already proved exterior measure, or maybe I don't have to scroll up, but contrast with fact that the exterior measure of a set E was equal to the inf O, where inf over all open sets O containing E. So remember, I just wanted to emphasize that this is different. This requirement is different from just saying that, just giving this characterization of exterior measure. And in particular, this is going to be enough to exclude the weird non-measurable set that we constructed in the beginning. Okay, so property. So now let's we've defined measurable set, but now let me tell you. So I told you the set's measurable. Let me now define the Lebesgue measure. So definition: if E in RD is measurable, its Lebesgue measure mu is given by, or just is, so I'm running out of room on this page, is mu of E is equal to mu star of E. So if a set is, so the punchline is that we've built the Lebesgue measure. What was missing is just given by the exterior measure of a set. What was missing was this definition of measurable. So once we declare sets are measurable, then we measure them via this exterior measure. Any question about this definition? It should look a little subtle at the moment, and hopefully it'll get clearer as we work through it. Work through a lot of examples and improving properties. Any questions at the moment? Okay. So properties. Property 1. Every open set is measurable. Right? Obviously from the definition, because we could just take this open set O to be E itself, right? And then we would just be measuring this property. It would contain it, and then we'd be just measuring the empty set here, taking the exterior measure of the empty set. So every open set is Lebesgue measurable. Observation, maybe this is property 0, I'm sorry, maybe I should have put this before the first one, is that mu inherits what I called properties 1 through 5 of that we proved for mu star, right? It inherits all the properties of mu star, right? Because the measure of a set is just its exterior measure. So the properties that we were proving before for exterior measure also hold for the measure of the set. They're the same thing for those sets that are measurable. Property 2. If the exterior measure of a set is 0, this implies that the E is measurable. So all sets that have exterior measure 0 are measurable. And then these sets that have measure 0. In particular, if all subsets of sets of exterior of have measure 0 have measure 0, if F is inside of E and the exterior measure of E equals 0, then F is measurable. And has measure 0, right? So this requires some argument. By what did I call these before? By I think I may have a labeling issue. Maybe I should have called these something else. So I'm going to use property 3 for exterior measure. For exterior measure, for every epsilon bigger than 0, so remember the exterior measure can be obtained by taking info for all open sets containing the set, right? For every epsilon equals 0, there exists an open set O with E inside O and mu star of O less than or equal to epsilon, right? We're assuming the exterior measure of E equals 0. So there's an open set which has measure epsilon, which contains E. But now, since O minus E is just equal, is a subset of O, monotonicity of the exterior measure implies that mu star of O minus E is less than or equal to mu star of O, which is less than or equal to epsilon. And now we're done, which implies that E is measurable. Okay, and the same, this observation about subsets of sets of measure 0 being measurable just inherits this, the same argument works for this second part of the statement here. Does this make sense? So sets of exterior measure 0 are measurable and they have measure 0. In any subset of a set of measure 0 has measure 0. So in particular, there's no crazy thing going on where you have really small non-measurable sets somehow. It's measure zero behaves as you would sets of measure zero behave as you would expect they would. If you have a subset of a set of measure zero, then a zero measure. If exterior measure of a set is zero, then that set's measurable. A consequence of this, so now consequence, one example that we had, the C Cantor set is measurable, and the measure of the Cantor set is zero. Okay. Remember, we proved that the exterior measure of the Cantor set had to be zero. So therefore, it has measure zero. It's measurable and it's measure zero. What am I doing? Property 3. Countable unions. Of measurable sets. Measurable. So we can now start trying to think of the collection of measurable sets as an object, and this is property 3 is telling us that the collection of measurable sets is closed under countable union. So we're going to try and deduce some properties of the set of measurable sets. It's closed under countable union. So the proof is that if E is equal to the union from j equals 1 to infinity of ej, ej measurable, for every j, select an open set oj such that E is inside oj, and the exterior measure of oj minus ej is less than or equal to, you guessed it, epsilon over 2 to the j. We do this for each of these sets in the countable union. This means that E is inside of this union of the OJs. And O minus E is inside the union of EJ minus oh, it's nonsense. Oops. No. OJ minus EJ. So by monotodicity, let's call this O, sorry. So this is the union of all the OJs is another open set, right? Openness is preserved under countable union. So the measure of O minus E, where this is O, is less than or equal to the sum of the exterior measure of OJ minus EJ, which is now less than or equal to epsilon, right? Because I just sum up epsilon over 2 to the j. Okay. Property 4 is that closed sets are measurable. So sets that are either open or closed are measurable. So let's argue this. So one, it suffices to show for so we'll show it first. We'll show it first for closed and bounded sets. Closed and bounded sets. Yeah. And this suffices, right? Suffices since every closed set satisfies F is the union of all F inner BKs where BK equals a closed ball of radius K, say. So you can write every closed set as a union of compact sets just by intersecting the set would just take increasingly large balls, radius K closed balls, and intersecting that with a set, and then taking a union over all those, and you recover the closed set again. So this will be the ingredient from passing from compact sets to closed sets. So once we show, since we can write every closed set as a union of countable union of compact sets, then once we show this property that compact sets are measurable, we can apply the previous property by saying, okay, well, we can just take a countable union of compact sets, we obtain every closed set, and so then thus every closed set's measurable. Okay. So now suppose F is compact. So its exterior measure is finite. All right, a closed or bounded set is a finite exterior measure. Let epsilon be bigger than 0. And property 3 of exterior measure means we can find open sets or an open O, and such that F sits inside of O, and mu star of O is less than or equal to mu star of F plus epsilon. Right, remember, because the exterior measure is given by taking info for all open sets containing that set. So to find such an open set for F, F is closed implies that O minus F is open. Right, this is the complement of a closed set's open. So confined, so means an almost. This property is quite tricky to prove. We're kind of using everything that we proved before. We can find an almost disjoint union of closed cubes Qj such that O minus F is equal to the sum from j equals 1 to infinity of Qj's. Now, for each fixed n, the kn, the union from j equals 1 to n of qj is compact. Right? As long as I take finite union of closed sets, I still get a closed set, right? And this, since each of these is compacted, so a finite union of compact sets is compact, still compact. So therefore, the distance between Kn and F is positive, since both are compact. Right, if you have two compact sets that are disjoint from each other, right? So why are they disjoint? Well, O minus F, this collection is the complement of F, right? And then I'm taking something that doesn't quite cover that complement of F. And it's compact, F is compact. So I have disjoint compact sets that the only way that this happens is if their distance is positive. So since K union F, so K, let's take K equals no, so Kn. Sits inside O. This means the mu star of O is bigger than or equal to mu star of F plus, this is Kn, mu star of Kn, which is equal to mu star of F plus the sum from j equals 1 to n of mu star of Qj. And therefore, the sum from j equals 1 to n mu star Qj is less than or equal to mu star O minus mu star F, which is less than or equal to epsilon by construction. Remember, this is how we chose O in the first place. It almost gave us the full measure of almost realized the infimum. Okay, so now let n go to infinity. Implies the sum less than epsilon, which therefore remember what these kns are, what these qj's do. This is equal to the set. So then by countable additivity, this is less than or equal to the sum from j equals 1 to infinity, which is less than or equal to epsilon. So now you see that this argument was quite difficult, right? We kind of threw the kitchen sink at it, but we've been gradually building to this. So closed sets are measurable. And let me think. All right, the next property is that the complements of measurable sets are measurable. But I think I'm going to save that till next time, as I think 5 minutes might be a bit rushed to do the next property. Yeah, so we're what we're doing is we're building, we're showing the structure of the collection of measurable sets. Right, it's a nice class. it's now we've showed it's preserved under countable union. We showed that closed sets, open sets are measurable. We showed that closed sets are measurable. Next, we'll show that the complements of a measurable set is measurable. And we'll show that countable intersections of measurable sets are measurable. So measurability is going to be, we're working to show that this is closed under all the operations of set theory, the typical operations of set theory. Okay, any questions at the end of the class here? I can stay for a couple of questions, especially since I have to miss my office hours today.
Well, I have a question, although it's quite broad. It's not really about these properties in particular. So we define the Lebesgue measure based on the exterior measure, which we defined in terms of like volumes of closed cubes, which is related to the product of a bunch of lengths of intervals. Does it really matter how we define, like could the way we measure those lengths of intervals be any metric, or does it have to be like the regular metric?
I see. So did we have to start off like this and build a measure from length of interval? So no. And in fact, it'll be, so I'm going to like slightly different, answer your question in a slightly different way, but what will, so if you took a different class, you might start off with defining a measure as something satisfying a bunch of abstract properties. And what we did here was we built a particular measure. And it turns out that this is kind of like, it's a little bit nicer. I think it's much nicer, in fact, to go this way, where we start off with something we understand, like volume of a cube, and build a measure, and then later observe, and this is kind of historically how it happened too, and then later observe, well, like functions, so measures, so this object of measure, an object with this property is kind of interesting in its own right, and this theory that we're going to develop, this integration theory, is going to be built from the notion of a measure, and then we could have different, it ends up that this is going to be quite flexible. And so there's in fact many different types of measures. We're dealing with real valued measures. So the measures we're getting are spitting out real values, positive real numbers. You can drop that assumption. You can allow your measure to take negative values, etc., which will be quite useful. You can even let your measure be complex valued. So a measure doesn't even have to be take a real value. So they're complex measures. And so it actually is quite, it turns out that the object we're going to build in an abstract sense ends up being quite useful. And one example that where we can put everything, you can put a lot of things in the framework of the integration theory we're going to build. For example, in calculus or in your analysis class, we studied summing series, right? And infinite, remember there's some similarity. It seems like there should be some similarity or analogy between summing a series and computing an integral. And it turns out that you can put them both on the same footing just by putting what's called the counting measure on the natural numbers. And then this theory of series becomes a theory of integration for the counting measure. So there's a lot of, there's another thing called like the delta measure, which is related to the object that when we were constructing this approximate identity. And the delta measure will assigns to every set 0 that doesn't contain the origin, and assigns to the origin any set containing the origin the measure 1. So there, and it turns out that this kind of extreme object will satisfy these nice properties of measure that we're gonna prove for the Lebesgue measure. So the theory ended up being quite a nice theory, in that there's a lot of things fits in this framework. But you're exactly right. Like we're generalizing volume here, but the thing that we ended up with can be seen as sitting in a larger family of more abstract objects called measures. Yeah, so not every measure generalizes any notion of volume. That the Lebesgue measure though is the measure that coincides with our notion of volume that our intuition. What's nice about this doing this first is that it's intuitive, right? There's some intuition here. Whereas my first measure theory class, like I started off with a algebra, a ring of sets and algebra, and I had no idea what was going on for a long time, years in fact.
A measure is something that acts like a measure.
Yeah, exactly. And I was like, what? A ring of what? Excuse me. So this book actually this in your book in this you can look at a later chapter where it starts covering abstract measures, but it starts with this construction, which is I think really nice. It's a really nice book for this reason. Any other questions?
Can I ask, can we possibly change the definition of measurable set in some sense so that we actually assume that all measurable sets are satisfying the finite additivity property in some sense?
I see. So rather than defining a measurable set like this, you'd rather, and then try to prove that finite additivity property, you'd rather start with saying I only want to consider sets for which this finite additivity property holds and declare such sets to be measurable. Mm-hmm. I don't know. I don't know. I don't know. It might be the case that it might coincide. I'm not sure, but it sounds like it might be hard to prove other properties about measurable sets if I just take that as my definition. You'll somehow yeah, I'm not sure, but what makes a definition useful, kind of, just in general, is the ease from which you can see other properties from it, other properties that you might want from it. So maybe give that a try, if you'd like. Does that make sense? Give it a try. Like try taking that to be your definition and see what you get. I think the thing that we're shooting for is that this measurability is closed under the normal operations of set theory. So if you can deduce everything you want from that definition, or from a different definition of measurability, then you probably end up with the same thing.
I see.
Yeah, so off the top of my head, I'm not sure if that would be enough to prove everything else that we want to do. Mm-hmm. All right, guys. I've any other quick questions? We've got to run in a second.
Thank you.
Thanks.
Thank you.
Okay.
See you.
See you.